let's go ahead and do it that way.
Is he so true?
I know we have to get rid of mass somehow. So if I solve for mass using this equation, so I have mass is equal to y cosine theta minus mu s y sine theta divided by g. I can plug that into here. And now I have one equation, two unknowns. Which typically is bad news. Let's see, so cosine plus sine. So I get mu s y cosine theta plus y sine theta.
Could you repeat the formula for mass again? Or can I repeat mine to you and you tell me if it's right? Okay, good, thanks.
Y cosine minus, so this would be y cosine minus theta minus mu s y sine theta over g v squared over r. Dropping back. Right.
Okay.
Why don't I go ahead and distribute? U s y cosine theta plus y sine theta equals y cosine theta over g v squared over r minus mu s y sine theta over g v squared over r. That's the magic thing that will suddenly make this solvable.
Is it?
Can we substitute mu, so that's,
We can stick a number in for it, but
it won't help?
not yet. I still have, my two unknowns are the normal force and the speed. But I have one equation.
Do we need to put an angle?
That still doesn't eliminate an unknown.
Do we just solve for the unknown by moving stuff around?
Yeah, but we have two unknowns.
Can we cancel out mu sub s?
No, there's no mu sub s here, no mu sub s here.
Oh my god.
We could multiply both sides by g and r.
We could,
Would that help?
it depends on how you go about solving it. To me, I would rather get rid of the fractions, so I would,
Okay.
so mu s g r y cosine theta plus g r y sine theta equals y v squared cosine theta minus mu s v squared y sine theta. To me, it looks cleaner, but that's on what your taste is.
Okay, it's like.
Can we not cancel out the y's?
Yes. Every term, we have 4 terms here. And remember, terms are added or subtracted, factors are multiplied or divided. I guess technically just multiplied. But I have 4 terms, every term has a y in it. If I multiply everything by 1 over y, the y's cancel out. Cancel, 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 cancel. And now I'm left with one unknown, v squared. And so v squared is equal to mu s g r cosine theta plus g r sine theta divided by cosine theta minus mu s sine theta. At this point, we have an equation for v, if I take the square root of both sides, and now I have an equation for my speed.
G equals 9.8 again?
Yes, so I have 0.7 times 9.8 times 100 times the cosine of, what did it make, 20 degrees, plus 9.8 times 100 times the sine of 28 degrees.
28 degrees.
28 degrees. Over cosine of 20 degrees minus mu s sine of 20 degrees. Oh, I know what mu s is. 0.7. We will end up with a positive number.
On the top, is that 100 or 0.1?
Start again.
On the top, is that 100 or 0.1?
That's a 100. That's a 100.
So we're solving for V now?
Yes, officially we're solving for v the entire time.
Okay.
Yes, that right there, cosine 20 degrees.
Could you make it look more like a 20 than a 6?
We will find out.
Thank you.
I got V equals 37.4.
77.4,
37.
37.
Oh,
Oops,
Oh.
not degrees.
At least a 15% chance I did it wrong.
Which is probably just shy of 80 miles an hour. A 20-degree bank is also rather steep,
Yeah.
so just be aware of that as you're going around curves in a car.
Most of them are 20 degrees.
Pardon?
Most of them are 20 degrees. Why? Because I've been on a 20-degree bank, and it feels like you're gonna fall out. Especially if there are no doors, like I was.
I don't.
In a Jeep?
Yeah. This dude was taking me. So my sister has this rich friend because yeah. Anyway, so he's taking us to his boat to like go on a boating date because he's like that, and he decides that since we're carrying such heavy equipment that we're gonna take the Jeep the total of like 100 feet to the boat, and there was a hilly area that we rode over, and it was like I would have rather just walked.
Well, I'm glad you survived it.
Thank you.
This is chapter 5. I
Any questions?
Can we cancel out MU? Sorry, mu?
No, because looking at this
Because it's
version,
not in all of those things.
yeah, these two
Okay.
terms don't have mu in it.
Okay.
Now, we could have saved a few steps. There's another thing that we could have done to save a few steps.
There you go, it just doesn't have.
So I'm going to drop back for a second.
Sorry.
If instead of bringing y cosine theta over, if we brought weight over, or somehow got weight separated from it, so I have mu s y cosine theta
Okay.
minus y sine theta is equal to mv squared over r. And then down here, keep mg isolated and take everything else over, so I get y cosine theta minus f sine theta. Oops. Mu s y sine theta. Now, if I factor y out, I'm left with mu s cosine theta minus sine theta equals mv squared over r, and then y times cosine theta minus mu s sine theta mg. Divide, so basically what these two equations, then divide, y's cancel out, m's cancel out all at the same time, and then if I multiply both sides by rg, I have my equation for v squared, which is what we got there, just an alternate way of doing it.
That's what I thought we were.
I kinda like our way better.
Do I like the other way better? All right,
It's too many lines.
Yeah.
Because that's what we did for the last one.
all right, any questions before we hit that last topic of chapter 6?
Can you wait for me to calculate it so I have it right now?
I thought he divided it. I was kind of hoping we did it.
And obviously, we could set a different problem in what is the minimum speed.
How would we find that?
What are we?
The only difference is friction flips
Like the directions?
directions.
Did we all get 37.405? Okay.
All right, gravitation. We so far, when we've talked about gravitational force, we've talked about weight. So we have a small object next to a huge object like a planet or a moon. We have a nice little formula of mg. But if I want to talk about, say, the force between you and the book next to you, mg is not really going to work particularly well. The force from the Earth is so incredibly much more powerful than between you and a book that those forces we just ignore. Or if we're talking about planetary forces, Earth, Moon, what is the force between them? Well, if you know the mass of the Moon and you know the acceleration due to Earth's gravity as the Moon goes around it, yeah, you could use mg still, but g is not 9.8. So there must be a more general formula for gravitation. I know it has something to do with the masses. So it's a requirement, an object has to have a mass. And I know that the magnitude of the force between them is the same. The Earth pulls on the Moon with the same amount of force as the Moon pulls on the Earth. So whatever I'm doing with the masses, commutative property has to hold.
So F sub g is different than weight?
F sub g is the general form of the force due to gravity. mg is a specific case.
Can we use this form instead of mg?
Yes.
Is it inconvenient to do so?
If you know what little g is, then this is, I think mg is a lot more convenient. But however your mind is working at the time. I know that the larger the mass is, the more the gravitational pull is. So whatever the mass is, it's going to be in a numerator. And commutative property holds, and I have two operations where commutative property holds. I got multiplication and addition, and it turns out it's multiplication. So the force due to gravity has something to do with the product of the two masses. And I've left space there for additional things. So if you imagine that this gravitational force is given off by, let's just say that the Earth is giving off some gravitational pheromones that the Moon is sensing. If that's the case, if the Earth is giving a pulse of what we now call gravitons outwards, then the farther out you go, let's say it gives a pulse of, let's say, billion gravitons. Well, the farther out you go, the fewer gravitons there are per square meter. That gravitons gets spread out over a much larger distance as that pulse expands. So it's like throwing a rock into a still pond. You get much larger ripples at the beginning, but the ripples die out as you get farther away. So it would make sense then that the gravitational pull gets weaker the farther away you get. Matter of fact, it should get weaker, somewhat related to the surface area of this ever-growing sphere. And so there's an r squared on the bottom.
R squared is in radian? Or, sorry.
And radius, it's the
radius,
distance
that
between
thing.
the two objects, center to center.
One R is radius, R80 is radius.
Yeah, I meant to say radius, but I was thinking about my arm, so.
All right, now I've left the gap up front. It comes down to the unit system. That F is in newtons. I have two masses here, which are both kilograms. I have this, which is meters squared. Whatever this is, it has to have units of, well, let's just solve it like an algebra problem. If that's, so I have some mystery thing right here. So the units of this must be equal to the units of my big G there times the unit of mass squared over the units of distance squared. So I have newtons is equal to my units of G times kilograms squared over meters squared. Therefore, my units of G in SI units would be newtons, meters squared, or kilograms squared. Now, there are other unit systems where the value is different. There's what's called the generalized unit system where G is equal to 1. That's of the philosophy that since the units can be anything we want them to be within reason, let's just make it a unit system where big G is equal to 1. Those same people will have the speed of light equal to 1. Which is really annoying when you're trying to relate it to two different textbooks. And this equation, this book says E equals mc squared, and this book just says E equals m.
That's irritating.
Yeah, I found it so.
So FG equals M? Or N?
The units, this is the symbol for the units of, so the units of force, if I'm in SI units, is newtons. So this turns out that big G is known as the gravitational constant. And I am parenthetically going to write universal. Because older textbooks called it the universal gravitational constant. It is now questioned whether it is indeed universal, but it does seem to be true for what we can measure.
Can you remind me why R squared is on the bottom?
Because whatever is creating this force, this gravitational force, is spreading out. And so whatever is communicating this force spreads out over the surface of a sphere, which is proportional to the distance squared. It gets basically whatever.
So distance between the objects is proportional to distance squared?
The force between the objects is inversely proportional to the distance squared. And so G is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared.
So force between two objects is proportional to distance squared. That's what you said?
Inversely proportional.
Inversely.
So it's on the bottom. And another thing that students sometimes will just call gravity, which is why I get really picky about that. It is just an aspect of gravity.
Big G or little g?
Big G.
Or,
Little g is an aspect of gravity also. But I have had students call weight, generalized gravitational force, gravitational constant, and acceleration due to gravity, all gravity, and I get tired of that.
is it that they're wrong or that, excuse my language, that you're maybe just a little bit nitpicky about it? Cause like
Yeah,
in class.
gravity
we
is a
say-
huge topic.
Yeah,
So calling them all gravity, calling them all the same name,
weren't you
is-
just complaining about, weren't you just a little irritated that they call it different things with more words when it's all just gravity?
no, I was complaining the fact that they were all calling it gravity, when they are
Oh.
different things.
Sorry, my bad.
Now, obviously, force is a vector. This is not the formal definition of it. If I have two forces here, they are attracted to each other. And so, let me introduce the radial unit vector. I feel like I've talked about radial unit vector before. Looking for some look of recognition.
No.
So one person, no. All right. The radial unit vector symbolizes R with a hat. It is indeed a unit vector, that's the hat. It's a unit vector, so it has a magnitude of 1. It has no units itself,
And
well,
is it
like a
rel-
unit vector.
is that important to those two circles with the arrows pointing at each other?
Yes,
Okay.
it'll connect. And the direction, with I hat, you pick a direction, this is the I hat direction. J hat is perpendicular to that, K hat actually is set once you've established I and J. But with the radial unit vector, it is away from the center.
Ah. Yeah. Got it.
So if I wanted to indicate towards the center, it's negative R hat. Yes, Stephanie?
So when you mean towards or away from the center, is that where, like, in that demonstration, the two arrows would meet, or the forces themselves?
Alright, so if that's mass 1 and mass 2, then the force due to gravity on mass 1 from mass 2. So it's the force